Hi class, this video is on topic C7, radioisotopes and radioactive decay. So depicted in this artwork is Marie Curie, a famous scientist who made significant contributions to science, and specifically she added two elements to the periodic table, polonium, and she named it this because of her Polish pride, and radium, named after the rays that were emitted from this element. And these are two elements that have isotopes that are radioactive. So that's how it fits into this lesson. And also, interesting fact, Marie Curie is the first woman to win a Nobel Prize and the only person ever, man or woman, to win two Nobel Prizes in two separate sciences, chemistry and physics. So before we start talking about radioactivity, we have to just kind of review what we sort of know about nuclear energy. And we know that it's energy released by a nuclear reaction. And releasing nuclear energy would be releasing the energy from deep within the nuclei of atoms. So this is a form of potential energy or stored energy. It's stored in the atoms. And there's three ways to release nuclear energy that we're going to be talking about in this course. And the first one is the focus of today's radioactive decay. And then nuclear fission and fusion are the very last video of this unit. So where have we seen nuclear before? In Unit 3, we talked about nuclear energy being a form of potential or stored energy. And it's energy possessed by nucleons in the atomic nucleus. And nucleon, we haven't started to use that word in previous units, but nucleon refers to protons or neutrons. So the subatomic particles that are in the nucleus are called nucleons. And then even before that in Unit 2, we talked about the strong nuclear force, and it's one of the four fundamental forces. This was just very briefly, we talked about the very strong force of attraction between the nucleons. So in order to really understand this lesson, you might have to forget what you know about chemical reactions. Well, not forget, but let's put them side by side to completely compare similarities and differences. So in chemical reactions, bonds are formed or broken. But in nuclear reactions, there's no bonds between electrons. It's not two atoms that are attached by a bond. It's nuclei emitted or and these, the nucleus or nuclei in plural is going to release or emit either particles or rays, energy rays. So what happens to the atoms? So in chemical reactions, the atoms don't change identity, but they're just rearranged. Nuclear reactions, the identity of the atoms change. We start with carbon, we end up with nitrogen. In chemical reactions, you start with carbon, maybe in a glucose molecule, you'll end up with carbon in a carbon dioxide molecule. So you don't lose the carbon, but in nuclear reaction, that carbon actually turns into nitrogen. In chemical reactions, it only involves electrons. In nuclear reactions, it could involve any of the subatomic particles. Chemical reactions are small energy changes. Nuclear reactions are larger energy changes. And there are differences in what affects the reaction rate. So let's go way back to maybe even grade 9 science to review what is an atom. So looking at one model of an atom, we see the subatomic particles, electrons, protons, neutrons, and recall that protons are the positively charged subatomic particles, neutrons are neutrally charged, and the protons and neutrons together are the ones in the nucleus. They're called nucleons. The electrons fill up the space in between atoms in the electron clouds, and they are negatively charged. And if we just look at a model of this element, we can tally these up. And we can see 13 protons, 13 electrons, and 14 neutrons. The fact that the number of protons and electrons are equal tells us that this is neutrally charged. It's not positively or negatively charged. It's not an ion, it's just an atom. And then 14 neutrons, 13 protons, those are located inside. So once we've done that tally, you might say, well, which element do we have, besides the fact that it's written here? So which number do we look to identify the element? It's the proton, number of protons. So 13 protons, it means we have aluminum. We go to the 13th element in the periodic table. So drawing the model takes up too much room and time. Instead of counting from the diagram, we're going to look at shorthand notation. So there's the periodic table notation, which we use a lot in chemistry, and then nuclear notation, which you're going to need for this course. And the smaller number, the smaller of the two numbers, is the atomic number, which is the number of protons. And as mentioned, the number of protons is what identifies the element. This is the 13th element in the periodic table, called aluminum. It is unique, and this is similar to when I'm teaching it in grade 9, we say, well, like a jersey number identifies a player on a certain team. So let's say on this team, the ref calls a foul on player 13. So you know it was James Harden if you knew that that was his jersey number. So in the periodic table, no other element has proton number or atomic number 13. So if I don't tell you that it's aluminum, I don't give you the symbol, I don't give you the symbol or the word aluminum. If I just tell you it's the 13th element, or I say this element that I have in mind has 13 protons, then it identifies aluminum. And in the periodic table, no other element has 13 protons. All aluminum atoms have exactly 13 protons. And while having 13 protons is always true for aluminum, it's not true of the number of neutrons. You can have a different number of neutrons. We have like 14 neutrons in this example, but we can have different versions of aluminum through changing this number. And these different versions are called isotopes. And mass number, it's the bigger of the two numbers, is the sum of the protons plus neutrons. And so different isotopes have different mass numbers. And we can distinguish which isotope or which version of an element we are referring to by this mass number. So for example, this is, okay, so the nuclear notation is what we're using in this course. This is the one you need to know with a bigger number on the top. And we'd say this is aluminum 27. So this is the version of aluminum that has 27 nucleons. And you might wonder why the chemistry notation has the bigger of the two numbers, which goes on the bottom in this case, even though we put it on the top. So why is it a decimal value? Why isn't it an exact number? Because we always work with whole numbers with the atomic number and the mass number. So if you recall from previous science courses, this number is the average atomic mass. It's a weighted average of the mass numbers of the isotopes found in nature. And if you round the average atomic mass to the nearest whole number, you usually get the mass number of the most naturally abundant version of that element. For example, we round 26.98 to 27 to get to the nearest whole number. And in fact, aluminum 27 is the most naturally abundant isotope of aluminum. And in nature, a very tiny fraction of the aluminum that's found in nature is aluminum 26, which is why when the calculation is done, that considers its abundance and its mass, we get a number that's a little bit lower than 27. So let's do an example. So an atom has a mass number of 234 and an atomic number of 90. Determine the number of protons, electrons, neutrons, and identify the element. So you might want to put a post-it for page 664 in your textbook because that's where our periodic table is. So are we going to use the number 234 to look up what the element is? Okay, well, let's go in order. So the number of protons, how do you get the number of protons? It's the atomic number. So it's 90 protons. And then there is no mention that this is an ion. So it's assumed to be neutral, then it's 90 electrons as well. The number of neutrons. So take a moment to think, maybe pause this video. Do you remember how to get the number of neutrons from grade 9 science or grade 11 chemistry if you have it now? Okay, so we take 234, which is protons plus neutrons, and we subtract 90. So if 90 is protons, then the rest is neutrons. So 144 neutrons. Now, which of these three numbers do we look up in the periodic table? It is the number of protons. So this is what identifies this element as thorium. And the symbol is capital T, lowercase h. So you might notice that the average atomic mass of thorium in the periodic table is 232.04. So it's not 234. So that means 234 is likely not the most naturally abundant form. Although thorium-234 is a common product of the of a nuclear reaction we're going to talk about later in tomorrow's video. So let's talk about review of ions. So this is not something we're going to talk about a lot in this course, but it's important that we distinguish changing up the sort of regular atom version from the periodic table in different ways. So if an element has fewer or more electrons than the regular atom, it becomes a charged ion. So if we add electrons, we become an anion. If we remove electrons, we become a cation. So ions have to do with more or less electrons. But then there's other, I call these like atomic upgrades, like changing it from its base, regular version from the periodic table. So instead of changing the electrons, we could change the number of neutrons. So if we change the number of neutrons, those variations of the element, they're called isotopes. So one of the famous couple of isotopes are for hydrogen. So for hydrogen that only has one nucleon, hydrogen 1, this is naturally occurring, most abundant. If we increase one extra, this is one proton and one electron. It's the only element in the periodic table that has 0 neutrons. Now if we add one neutron, so now it has 2 nucleons, so it's hydrogen 2. This is naturally occurring and important in nuclear science. And in fact, it's so important in nuclear science, it's given a nickname, deuterium. And this could even be the hydrogen that is in the H2O. So that's called deuterated water, H2O. And then we can add another neutron, and this is only human-made, and it's useful in nuclear reactions. This is hydrogen 3. It's also so important in nuclear reactions that we gave it a nickname, tritium. Okay, so let's just take a look at the GIZMO, which will help us practice this. Okay, so let's say we want to look at, the GIZMO starts like this. We're going to turn on abundance in nature, and we're going to turn on the symbol. Let's focus on carbon. So we started with carbon 12. This is by far the most naturally abundant. So if you take a pile of carbon, most of the pile of carbon is the atoms have 12 subatomic particles in the nucleus. So if we were to count these up, we will get 12. And it's actually, because it's the 6th element in the periodic table, it's 6 protons, which is red, and 6 neutrons, which are gray. And then this blue cloud is representing where the electrons would go. So now what we can do with this is we can peel away, we can have one less neutron. It's unstable, carbon 11, and it's really not abundant in nature. That doesn't mean that it couldn't be created. So let's go back to carbon 12. Let's see if we can add a neutron. So carbon 11 was one isotope. Carbon 12 is another isotope. Carbon 13, it's still stable, and it's present in 1% of the carbon in nature. Let's keep adding neutrons. Carbon 14 is very unstable, and it is present in a trace amount. Although you might say trace amount, that's so insignificant, why do we talk about it? But for carbon dating, it's quite important. And because it's unstable, there is a decay reaction that releases energy, so it is detectable even though it's trace amount. What happens, just for fun, to see if we add them all? It's very, very unstable. Okay, so let's go back to carbon 12. So adding or removing neutrons would be creating different isotopes. Okay, so some terms: a nucleon is a proton or a neutron. An isotope is a form of an element that has the same atomic number but different number of neutrons. Radioisotopes, it's an isotope, so one that has a different number of neutrons, an isotope that spontaneously changes nuclear structure and releases radiation or energy. So applications of radioisotopes, because they release energy as they decay, we can detect that decaying. So we can use it for carbon dating, which means we can tell the age of, for example, a fossil. If you find a bone in the ground, you could date that bone by saying, is it, I don't know, 1 billion years old, or is it 10,000 years old? Is it a bone that your dog dug up last week, or is this a fossil that belongs in a museum? So it looks at the amount of carbon 14 compared to the amount of carbon 12, because that ratio is set for a living object, and then once an object dies, that ratio changes in a predictable way. So it could also be used for tracers for detecting cancer or for treating cancer. Unstable nuclei and radiation. So some isotopes are unstable and change their structure, and to become more stable, they release energy called radiation. So isotopes that are going to release radiation are called radioisotopes. Okay, so radioisotopes can release energy to become more stable in a number of different ways, and these are different types. These are different types of radioactive decay. And here we have the nuclear reaction equations of, this is the general formula for each. It's not element X. There's no element X, but if X represents an element, it represents a radioisotope. So we put the element symbol, and then we use the larger of the two numbers, the mass number, at the top, and then the smaller of the two numbers, the atomic number, at the bottom. So the bottom number is that number that identifies an element. So whatever this is, let's say if this is 6, it tells us that this is carbon. This is called nuclear notation. I think I said that already. So another thing to notice is that we might emit a helium particle or an electron or a positive electron, or we might capture or kidnap an electron, or we might release gamma rays. So those are some of the differences and similarities that you might notice. 4 of them, the 1, 2, 3, and then 4, They might sort of look like a decomposition reaction in chemistry because you only have one starting substance. But here instead, notice that the atomic number or the identity changes. So element X turns into Y. This bottom number I said is the thing that identifies the element. So Z becomes Z minus 2, for example, in alpha decay. So in chemistry, we've said this before, if you had carbon on the left side, on the product side of the arrow, you'll always have carbon somewhere on the right side of the arrow. But here in physics, you might start with carbon and end with nitrogen. And given a radioisotope name and a number, you'd have to complete the the nuclear reaction equation. So you'd be given the radioisotope and you'd be told it's one of these 5, and you'd have to complete the other side. So we're going to look in more detail into each one of these. So the first type is alpha decay. The emitted particle is a helium nucleus. A helium nucleus, that is also called an alpha particle. And the problem is that a radioisotope is very heavy, so lots of nucleons, and the solution is that 2 protons and 2 neutrons will be chipped off element X to create the alpha particle. And it's a helium nucleus, not a helium atom. There's no electrons, but it's just the 2 protons and 2 neutrons. And notice that the atomic number and the mass number and the atomic number change in the process of alpha decay. So element X turns into element Y, which we never see in chemistry. So for an example, polonium, polonium-212 turns into lead-208 and releases a fast alpha particle. And this radioisotope of polonium is releasing nuclear energy and doing this and becoming more stable. So let's just go to our GIZMO and see that in action. So in this, I like to set up writing. I click write equation. I'm going to click alpha decay, and I want it for polonium. So I'm going to take a look at my legend. I've got protons and neutrons, the purple and gray in the middle, and just going to play and see what happens. So it's shaking to represent instability. Let's do it again. Shaking and representing instability, and 2 purple and 2 gray chip off, and there's gamma, there's energy released. So let's see that equation. Notice that our top number goes down by 4 because 2 protons and 2 neutrons. So it's 4 less things in the nucleus. The bottom number goes down by 2. So there's 2 less protons, which means you're going to go to the left in the periodic table by 2 elements to figure out the new substance. So lead is 2 over from polonium. Okay. Oops. So let's do an example. When radium-226 undergoes alpha decay, it produces a stable isotope. Determine the element and its atomic number and mass number. Okay, so, oops. So we're given the mass number. 226 tells us one of the numbers that we're going to use, 226, the top number. And then because it says radium, we write Ra, we look up in the periodic table to find out that it's 88 as the proton number. And then it says alpha decay. So as soon as it says alpha decay, I know it's going to be He42. And then I just do the math to see what's left. Well, if 226 has 4 pieces chipped off from it, from the nucleus, it becomes 222. And at 88, if you remove 2 protons from that 88 protons, you get 86. Then you look up in your periodic table that it is radon, or you could just move 2 to the left from radium. So radium 226 turns into radon 222 and releases an alpha particle. So the next type of decay involves the emission the emission or capture of a beta particle. And there's three types: beta negative, beta positive, or electron capture. So, the second type, the first type was alpha decay. Second type is beta negative decay. And the emitted particle is an electron, also known as a beta particle. So an electron. So for the top, you're usually writing a mass, but an electron doesn't have a mass, so you write 0. And then the bottom is like how many protons you have, but an electron is kind of the opposite of a proton, so you put -1. And then beta, Greek letter capital B with a negative, is an alternate way of writing this. So the problem is that you have a radioisotope with too many neutrons, and the solution is to take a neutron and turn it into a proton and an electron. One example is carbon-14 turning into nitrogen-14 and a fast electron. Okay, so let's see that in action. So I go to beta decay and I want to see it for carbon. I turn on writing my equation. I take a look at my legend. It does make sense since I've got carbon instead of, what was our previous one? Polonium had a huge nucleus. Carbon is not many in the nucleus, but what was the problem? It was too many neutrons. So 14 neutrons, that's a lot more than the stable carbon-12 that we are familiar with. So I press play. You can see that the neutron, the gray neutron, is turning into a purple proton plus an electron that is released. So if we show the equation, we can see what happens. Okay, so for an example, bismuth-214 undergoes beta negative decay. It produces a stable isotope. Determine the element and its atomic number and mass number. Write the nuclear equation for this beta decay. So bismuth-214, the 214 gives us the number on the top. We look up in the periodic table the number of protons and the symbol. As soon as it says beta negative decay, so I promised you that we'll give you the type, but as soon as you see that, you should know that means it releases a negative electron. And then what does it produce? Well, if this type of decay involves taking a neutron away and turning it into a proton plus an electron. So this number doesn't change because, yeah, you lose a neutron, but you gain a proton. And you gain a proton. So take a look at the math and make sure it makes sense with the general forms. Okay, the next type, we've got beta positive decay. Emitted particle is a positive electron called a positron. Well, it sounds like something out of Transformers, but it's true. So a positive electron is a positron. The problem was that there were too many protons or too few neutrons, and the solution is that one of the protons becomes a neutron and a positive electron. Notice that the mass number stays the same, but the mass number decreases by 1. So an example is fluorine 18 turns into oxygen 18 and a fast-moving electron. So we don't have an example for that one, but you have some in your practice problems. An electron capture is the next type of decay. And this is when an electron from the inner orbital is kidnapped into the nucleus. And the problem is that radioisotope has too many protons, but not enough mass to undergo beta positive decay. So the solution is that the electron is kidnapped and it combines with the proton to produce a neutron. So you gain a neutron, but you sacrifice a proton. So the proton number goes down by 1. The mass number stays the same, and you have to put the electron on the starting side, on the left side of the arrow. Also, I don't know why every year I see students writing an equal sign here, but you would never do that in chemistry, right? It's always an arrow from starting from this, and the result is this. So it's an arrow. An example is gold 195 kidnaps an inner electron and becomes platinum 195. Okay, for gamma decay, oh, I was going to show you this, the gold. Okay, so electron capture, I'm going to turn that on, and let's do gold. Let's write the equation, take a look at the legend, press play. So an electron comes into the nucleus, and the electron, let's play it again, and the electron and the proton turned into, so the electron and the purple proton turned into a gray neutron. So that's what happened there. Okay, our last type is gamma decay. So high energy excited states often occur after a nuclear reaction. So this is like an isotope that has been produced from some nuclear reaction, and it's in a high energy state as indicated by this star thingy, asterisk thingy. And a gamma ray, a form of energy, is emitted in this process, and this is the symbol for the Greek letter gamma. The problem is that the atom is in this high energy state, and the solution is that that energy is released. And notice the atomic number stays the same, the mass number stays the same. So this is maybe arguably the easiest one to write out. You just need to know that gamma decay is this. Okay, let's do an example. When dysprosium-152 undergoes gamma decay, its nucleus changes from an excited state to a stable state. Write the nuclear reaction equation for this gamma decay. So 152 gives us the number on the top. Dysprosium, we look up in the periodic table to get that it's 66 and dy. And it says gamma decay, so we're going to give it this asterisk, and it's only going to have one thing on the reactant side. And then we're going to write the gamma symbol because it said gamma decay, and nothing is going to change about the numbers or the symbols except omitting the asterisks. Okay, so that's all of them. So ensure that you know, or that you study the similarities and the differences, and learn how to complete these nuclear reaction equations given the radioisotope. Given the radioisotope and which of the 5 types, you should be able to complete the other side. So radioisotopes will naturally undergo this decay. So it happens naturally. And there is the release of dangerous amounts of energy. So depending on whether it's alpha, beta, or gamma, different protection is required, because if you are working with radioactive substances, your body would otherwise be exposed to this energy, and energy is the ability to do work. For example, doing work on your cell's DNA or other forms of damage on your body. So for alpha particles, to protect against alpha particles, a sheet of paper will block alpha decay. For beta decay, it requires glass or aluminum. For gamma decay, it requires concrete, lead, or steel. So obviously gamma rays are higher energy than beta or alpha. Okay, now we're going to introduce a tiny bit of math. So for radioactive decay, that's the process by which an unstable atomic nucleus breaks apart, often forming different atoms. And we didn't really go over why this happens, so that's appropriate here. So some isotopes are unstable because they have too many or too few neutrons within the nucleus. And if you think about it, protons are positively charged, and like charges repel, just like two north ends of a magnet. So there's repulsion. So why would those protons want to stay together? It's because of that strong nuclear force. So an isotope existing, there's a delicate balance between the repulsive electrostatic forces and the attractive strong nuclear force. So see page 324 for more on this. So half-life, this is where we bring in the math. it describes the average amount of time required for a radioactive material to decay to half its original mass. Let's take a look at this graph for carbon. So we always look at the graphs, look at the axes first with this graph. So here we have time units, and it's the number of half-lives. So I'll explain what that means in a second, but basically this is over time. And here it says the percentage of the original carbon-14 remaining. So let's say we start at time equals 0, we have 100 grams of carbon-14. When do we get to 50 grams? It's at 5,700 years. So after one half-life, the 100 grams has been cut in half. And then what would happen if we double that time? So now if it's, what would that be? 11,400, we've cut that 50 in half, or we've cut that 100 in half 2 times. And if we have 3 half-lives, that means you cut 100 in half 1, 2, 3 times, and you have 12.5 grams left. So let's say if you looked at a sample and it had 10% carbon-14 in it, you would go to this graph and you would move along here and you would interpolate this to say whatever number of half-lives, and that would give you the age of the sample. Or sorry, the sample was a living thing, and it would be the age of that fossil. So when that fossil was no longer living. So mathematically, that models an exponential decay, which you probably have done in grade 11 math, if you've had it last semester. So M is the original mass, M naught or M0 is the mass remaining, or sorry, M at this one is the original mass. So it's M naught, but you could think of it as M original. And you're going to multiply it by 1/2, but how many times you're going to multiply by half depends on the elapsed time divided by the half-life of the substance. So if we had 11,400 divided by 5,700, that was 2 half-lives. So the 100 grams of our carbon-14 graph would be cut in half 2 times because this exponent was 2. So hopefully that makes sense. What's really important about that equation is not so much that it has to be in SI units, but that these mass units have to match and these time units have to match. So the time and the half-life time have to be in the same unit. So if this is seconds, that has to be in seconds. If this is days, that has to be in days. If this is kilograms, that has to be in kilograms. Okay, our last example, we have strontium. Half-life of strontium-90 is about 28 years. If a 60.0 gram sample of strontium-90 is currently in the sample of soil, how much strontium-90 would be present in the soil 98 years later? Okay, so writing out our givens. We are given that originally we have 60 grams. We want to know after 98 years of time, what is our M value? What amount of that 60 grams is still left? So you know your answer is going to be lower than 60. And it also tells you the half-life is 28 years, about 28 years. So I find, at least with the first one of this example, a T-table is beneficial. So let's write out year and how much sample you have, because it's kind of easy to visualize the dividing by 2 when it's a nice number like 60. So after 28 years, we've cut it into half. After another 28 years, we cut that into half. And then after another 28 years, we cut it in half once again. So do you see how the M value is take your original number and cut it in half, or multiplying it by a half a certain number of times. So that number of times. And we want to know 98 years. So 84 is not long enough, but if we add another 28 years, 112 is too much. So we know our answer for M is going to be somewhere between 7.5 and 3.25. So this is kind of like getting a range answer, but we want to use the equation to get it exactly. Using the equation, Notice the units will match 98 years, 28 years, and 60 grams tells us that we'll get our answer in grams. So 5.3 grams is our final answer. Okay. Radioactive dating is a technique used for the determination of the age of certain materials like fossils. And now it's time for you to do some practice questions. So these are relatively quick questions, and there is a table for you to summarize the radioisotope, the particles emitted in different radioactive decay. So it's page 34 of the student notes package. So please make sure to fill out the exit ticket for this Google Classroom task and finish these questions. Check your answers from the back of the book and then post them on Google Classroom. Have a great day. Stay safe. Stay well.